So good morning to all. So today we will discuss about vibration of a one-dimensional diatomic molecule or a diatomic lattice. So here you can see that there will be two atoms at one lattice point. So we can call it as a two-atom basis. So what that means number of atoms in the primitive unit cell is equal to 2. So you can see that there will be two atoms, one having the mass m1, another having the mass m2. And we can also see that we can say that m1 is less than m2. Okay, m1 is less than m2, and that means m2 is heavier than m1, right? So when you see the frequency of vibration, so I am not going to derive that vibrational frequency corresponding to this diatomic body. Instead I'm just writing the vibrational frequency or the frequency of vibration of a diatomic molecule. One dimensional diatomic molecule is C into 1 by m1 plus m2. Sorry, 1 by m2 plus or minus C. C എന്ന് പറഞ്ഞാൽ it is spring constant. Okay, so that is into 1 by m1 plus 1 by m2 the whole square. Okay, minus there will be 4 sine square. So as to extend 4 sine square Ka by 2 divided by m1 m2. So this is the expression for frequency of vibration for a one-dimensional diatomic molecule, and this relation you can actually call a dispersion relation because it is a relation between omega and k. So we can also call this relation as the dispersion relation. Okay, so dispersion relation. And in one monoatomic lattice, we have seen that only one value of omega you can see for a particular value of k. So now in this case, you can see that for one value of k, you can have two frequencies. There will be two frequencies. So that means you can see that there is a omega square plus or minus is there. Okay, so there will be for a single k value you can have two frequency. So that is a positive value of omega will be there, so you can say that omega positive. So this is a frequency that is corresponding to optical wave or a optical branch. That means it is a wave of electromagnetic wave which is incident on a one-dimensional diatomic lattice. So the corresponding wave on the optical wave ആയിരിക്കും. So if it is omega minus, then that will be corresponding to an acoustical wave or rather mechanical wave. Okay, so നമ്മൾ acoustical wave or acoustical branch എന്ന് പറയുന്ന term ആണ് നമ്മൾ normally use ചെയ്യുക. Okay, so here now we'll examine the each one optical wave, what is optical wave case, and what is the case in the acoustical wave scenario. Okay, so first of all we'll just take the case of optical branch case. So here you can see that the omega square plus has a value. Okay, omega square plus has a value that is C into 1 by m1 plus 1 by m2. Okay, plus we have C plus, we have to keep it as plus, right? Plus 1 by m1 plus 1 by m2 whole square minus 4 sine square Ka by 2 divided by m1 m2 will come. Okay, m1 m2 will come. And now in this particular case we are actually addressing some limiting condition, that is we have a case of long wavelength. So we have particular limiting cases. We have long wavelength means that is it implies low frequency. Okay, low frequency. So we have a long wavelength or low frequency behavior we are addressing at this point, and that means if long wavelength means lambda is actually very large. Okay, it is actually very large value. That means k, the wave vector will be what? It will be tending to 0, we can say, because lambda is tending to lambda is tending to infinity, and that means the propagation vector is actually k is tending to 0. So that means this frequency of vibration in that scenario, it is actually you can write like this. What is 1 by 1 plus 1 by m2 plus C into 1 by m1 plus 1 by m2 will come, because this sin ka by 2 term will goes 0, because this k 0 ആവുമ്പോൾ sin square k by 2 എന്ന് പറഞ്ഞ this term goes 0. So ഇതിന്റെ root when you take it outside the root, so then you'll be getting c into 1 plus m1 m2. That means so you will be getting omega plus, we can write it as 2c 2c into 1 by m1 plus 1 by m2. So you can just write like that, 1 by m1 plus 1 by m2. At what condition? At k equal to 0. At k equal to 0. So that is the first case. You can see that is a long wavelength scenario. And in the second case, where I will be addressing, we have a short wavelength. We have a short wavelength in that scenario, and that implies we have a high frequency. We have a high frequency. Okay, and that means k is actually a very high value. K will be possessing very high value because lambda is very small. So that means you can actually say that sine square k by 2 has a maximum value, that the maximum value will be what? It will be 1, because sine square k by 2 can take the maximum value, that is 1, right? So it will be 1. So this equation, the frequency of vibration for an optical branch in that scenario will be 1 by m1 plus 1 by m2, okay, plus c into 1 by m1 square plus 1 by m2 square, plus this expression becomes sine square ka by 2, you can keep it as 1. So that is 2m1 m2 will be there, minus 4 by m1 m2 will be there. Okay, so this is the expression you are going to get. So how do I get that? This is 1 plus m1 plus 1 plus m2 whole square ആണ്. So അതിനെ നമുക്ക് എന്ത് ചെയ്യാം, we can actually write this like, okay, like this. So that means your omega square plus, okay, omega square plus becomes, when you 2m1 minus m2 minus 4m1 m2, that is you will be getting minus 2m1 m2 കിട്ടും. That is 1 by m1 square minus, sorry, 1 by m1 minus 1 by m2 the whole square എന്ന് എഴുതാം. So that is you will be having 1 by m1 plus 1 by m2 here, and the second term will be you can actually write it as 1 by m1 minus 1 by m2 the whole square. Okay, so this will be the expression, and if you take this term outside the bracket, you can actually write omega square plus, you can write like this, c into 1 by m1 plus c by m2, you can write like that, plus if you take this term outside the root, you will be having c by m1 minus c by m2 will be there, and that means these two terms get cancelled. Okay, so we'll get as omega plus is equal to root 2c by omega plus ആണ് m1. So at what value? At what value means k will have the maximum value, that is plus or minus pi by a at the brilliant zone boundary. Okay, and you can also see a case omega plus at a shorter wavelength scenario at a high value of k. You can see that the frequency, the high frequency, okay, high frequency of behavior of high frequency behavior of optical branch, it is depends on what? It is depends on m1. M1 means the lighter mass. Okay, the smaller mass is depend on the lighter mass. Okay, lighter mass. So it is depending on m1. M1 and the comparatively the smaller mass. Okay, and you can also see that this can take the value if sine square ka by 2 is tending to 1 means you can actually say that sine square, you can just simply take it as sine square ka by 2 is equal to 1. Okay, that implies this sine can take two values, that is equal to plus or minus sine plus or minus pi by 2 will come, because k means plus or minus pi by a. Okay, and you can see that in that scenario ka by 2 എന്ന് പറയുന്നത് എന്തായിരിക്കും, because ka by 2 എന്ന് പറഞ്ഞാൽ plus or minus pi by 2 ആകുമ്പോഴാണ് you will be getting the value 1. So you can say that ka by 2 എന്ന് പറയുന്നത് that is equal to pi by 2, that is k is equal to plus or minus pi by a, plus or minus pi by a. So this is actually I have said this k is equal to plus or minus pi by a is actually a Brillouin zone boundary. Okay, so this is actually a Brillouin zone boundary. Brillouin zone boundary. So you can see that at a Brillouin zone boundary, BZ means Brillouin zone boundary, the frequency depends on the lighter mass, the lighter mass one. Okay, smaller mass ആയിട്ടുള്ള m1 ആണ് അത് depend ചെയ്യുന്നത്. And also you can see that by comparing the earlier cases you can see that omega plus at k0 is actually greater than omega plus at the Brillouin zone boundary. Okay, that is k is equal to k is equal to plus or minus pi by a. So the value of omega plus at k is equal to 0 is greater than omega plus at k is equal to plus or minus pi by a. So that you can also see that representation also. So that is an important aspect, important discussion. Now we'll move on to the discussion for uh, case of acoustical branch. So what will be the scenario for acoustical branch case? So we are discussing about optical branch. So then the second case, you can see that that is acoustical branch case. When you get an acoustical branch, when you send a mechanical wave to a one-dimensional diatomic lattice, the correspondingly you will be getting an acoustical wave, a sound wave. Okay, so that means you will be getting a acoustical branch corresponding to that. So omega square minus, so the negative sign indicates it is an acoustical wave. So omega square minus is what? It is C into 1 by m1 plus 1 by m2. Okay, and minus C into, so this is how the expression will be, 1 by m1 plus 1 by m2 the whole square minus 4 sine square ka by 2 divided by m1 m2. Okay, so this is the expression of frequency of vibration for an acoustical wave, as you can see. And here also you can consider two situation. Okay, that is for a long wavelength. Okay, long wavelength, that means low frequency scenario that I already said. So in that case, lambda is actually tending to infinity. That implies k is actually tending to 0, or rather you can take it as k is equal to 0. And when you put k is equal to 0 in this expression, you can see that omega minus becomes 0. Okay, because k0 means sine square ka by 2 term will be 0 and this term goes 0. And if when you take 1 by m1 plus 1 by m2 whole square outside the root, so then you will be getting C into 1 by m1 plus 1 by m2 minus this term, that is goes 0. So you'll be getting a omega square minus എന്ന് പറയുന്നത് you'll be getting a 0 എന്ന് കിട്ടും. That means omega minus is equal to 0. So what it means, you can see that at k equal to 0, at k equal to 0, the frequency of acoustical branch will be 0. Okay, the frequency of acoustical branch will be 0, but we have seen that in the earlier cases optical wave branch case, but in the case of optical wave branch, the frequency will not be 0, will not be 0. Okay, it will be a finite value for optical wave, but an acoustical branch, the frequency of vibration will be 0 at a long wavelength where the wave vector is equal to k equal to 0 scenario. And now we okay, okay, and next case we'll take, again we are considering long wavelength. Okay, and here what we say that we are not saying that k is 0, we are not considering that k equal to 0. Instead, we are, again the scenario is like the same, lambda is tending to infinity, and now we are not taking k equal to 0. Okay, here exactly we are actually taking k equal to 0 as of like. Okay, uh, so we just say that we have a near behavior of, we can say that we have a we are actually analyzing the near behavior of k equal to 0. It's like almost 0. Okay, so in that case omega square minus will be having c into 1 by m1 plus 1 by m2, that expression that you already know, minus c into, you will have 1 by m1 plus m2 the whole square. Okay, minus sine square k a by 2, it is reduced to k square by a square. Okay, k square by a square m1 m2, like the expression will be reduced into this fashion. And that means this equation you can actually write it as 1 by m1 plus 1 by m2. This if you multiply this one, if you take c into 1 by m1 plus 1 by m2, if you take it outside this case, they'll be having 1 minus root 1 minus k square a square, k square a square by m1 m2, that is m1 m2 by m1 plus m2 whole square. Okay, so this is how the equation looks like in that scenario. So as you can see here, at that case, this equation further you can actually write like this, c into 1 by m1 plus 1 by m2, okay, into 1 minus k square a square m1 m2 divided by m1 plus m2 whole square, okay, raised to 1 by 2, like this. So if k is very small, k is very small, so we can say that k square will be very small. It will be very small value. So when you expand the second term of this equation, that means this particular term, if you expand by using binomial expansion, so you'll be getting that omega square minus is equal to c into 1 by m1 plus 1 by m2. So you'll be having 1 minus, this 1 minus will be there. Okay, when you expand the other term, 1 minus this term, if you expand, so it is like a 1 minus x raised to 1 by 2. So it's a binomial expand. When you expand, this will be 1 plus 1 by 2 k square a square m1 m2 divided by m1 plus m2, like it comes. Okay, so that implies this equation as goes on, you can see that when you solve this particular equation, omega square minus is equal to c into m1 plus m2 divided by m1 m2, okay, into if my 1 minus 1 get cancelled, 1 and 1 get cancelled, so these two get cancelled, so you'll be getting us k square a square, k square a square m1 m2 divided by 2 into m1 plus m2 the whole square. Okay, and that is equal to, that means these two terms get cancelled. What it remains is that we'll have c k square a square divided by 2 into m1 plus m2, 2 into m1 plus m2. So that means your omega minus will be ka c by 2 m1 plus m2 to m1 plus m2 raised to 1 by 2 will come. And you can see that here omega minus is proportional to what? It is proportional to k. That means it is a case of monoatomic case, because we have seen in monoatomic case also omega is proportional to k. So it's like a monoatomic behavior you can actually see in this case. Okay, so omega minus is proportional to k. So this is an expression for a long wavelength, low frequency, where k is very very small but not 0. Okay, first case we can consider that k is equal to 0, and second case k is actually very very small, not 0. In that condition, the omega minus, the frequency of vibration of a acoustic wave, is actually proportional to k എന്ന് പറയുന്ന expression കാണാം, where c is the spring constant, m1 m2 are the masses. m1 എന്ന് പറയുന്ന lighter mass ആണ്, m2 എന്ന് പറഞ്ഞ heavier mass ആണ്. And you can see another condition which where you can see what is high frequency condition. Okay, we have a high frequency situation. That means already we know that is short wavelength scenario. So the wavelength is short, so that is k is actually very high value, k is very high value. So that means you can as we consider in the earlier cases, sine square ka by 2 will be tending to 1. Okay, and you can say that k will be, can take the value plus or minus pi by o, which is the billion zone boundary condition as well. So that is omega square minus, here you can actually write it as c into 1 by m1 plus 1 by m2 minus c into 1 by m1, like we have written in the earlier cases. So this expression will be like this, and when you solve this equation, you will be arriving at that omega minus will be equal to root t c by m2. Root c by m2 will be the expression here. How to make it m2? So when you put this here, it is minus minus c into root m by m1. So this one c into c by m1 and c by m1 will get cancelled. C by m2 plus c by m2 will come here. So that is root 2c by m2 will come here. So we can see that for acoustic case, acoustic wave case, at zone boundary, k is equal to plus or minus pi by a. The frequency of acoustical wave or acoustical branch depends on the heavier mass, that is m2. Okay, so you can see that the frequency of optical branch and acoustical branch at zone boundaries are different, and there is a gap between them. Okay, and which is known as frequency gap. Okay, so then as we have seen that in two cases, okay, particularly at high frequency scenario, where you can actually see that the frequency of vibration of acoustical wave at high frequency and the frequency of vibration of optical wave at high frequency, which two have two different value. So if I can represent that in terms of a graph of omega versus k, so it will be like this. Okay, okay, so this will be the graph that you can see here. So here it is a graph between omega versus k. So you can also call this curve as a dispersion curve, and you can see that there is a gap between the first one, the top one is optical branch, and the bottom one is acoustical branch. And acoustical branch, we have seen that in the case of omega equal to 0 scenario, sorry, omega equal to very for the sorry, for a small value of k, for small value of k, omega minus is actually proportional to k. And we also seen that at k equal to 0, omega minus is equal to 0. That is the case for acoustical branch. And we have seen that the maximum value that you can see at the high frequency is that is root c by m2, which is depends upon the heavier mass m2 for acoustical branch. Okay, and you can see that these are the two brilliant zone boundary minus pi by a and plus pi by a. Now if you look into optical branch scenario, optical branch, the lower frequency is a omega plus is equal to root 2c by m1. Okay, and you can see the higher frequency is that is root 2c by 1 by m1 plus 1 by m2. So we have seen that this is the point where k is equal to 0. This is the point where k equal to 0 for optical branch, and this is the point where the brilliant zone boundary plus or minus pi by a region. Okay, these 2 points, and you can see that there is a gap between this optical branch and that acoustical branch, which is called the frequency gap. Okay, and which is this top of this region we call top of the band, and this bottom region we call top bottom band. Okay, so these are the minimal discussion we can actually obtain from this particular graph. And you can see that this particular graph represent the phonon dispersion or elastic wave dispersion in a diatomic lattice. So this is an similar curve we also seen in the case of monoatomic lattice. Hope you remember that. Okay, so there cannot be any phonon corresponding to in particularly in this frequency graph. Okay, so frequency gap, you won't see any photon. There will be no photon will be there in the frequency gap. So you can see that the difference between the bandwidth allowed for an energy band or a frequency width for an acoustical branch means that is root 2c by m2 up to this frequency of up to omega minus root 2c by m2, wherever frequency and m, it can allow the frequency up to this limit. Okay, so this is actually a frequency band also. Whereas in the case of acoustical case, you can see that the frequency uh, okay, acoustical case, the frequency of bottom band is root 2c by m1, top band also you can see. And what is the frequency bandwidth will come? So the bandwidth for an optical branch will be sorry, the bandwidth for an optical branch will be you can represent like this. Okay, the bandwidth for an optical branch will be there. And frequency gap, if I say frequency gap, what is the frequency gap? So that will be actually root 2c by m1 minus root 2c by m2. So you can see that this frequency gap is depends on both m1 and m2. If we can see in a condition where m1 is equal to m2, and that condition you can see that the frequency gap will be 0. Okay, that means if both the diatomic molecule m1 and m2 having the same mass, then the frequency gap will be 0. If the frequency gap will be present if m1 and m2 are different. So you can see that this is how you will find the frequency band, and you can see the band width of a optical branch as well. Okay, so that is also an important discussion here. So you can see that this frequency band will give you what is the allowed frequency of frequency range for a propagation of wave in optical branch and in acoustical branch. Okay, so the band frequency will tell you what is the allowed region. Okay, and you can also see similarly for acoustical case also what is the band region will be. Okay, and now here you can see uh, mainly we have two branches left. We have optical branch and acoustical branch, and when you consider the frequency gap of and that is proportional to what, it is root m2 by m1, one can say that. Okay, by that expression. And you can see that if the value of m1 increases, the gap will decreases. If the value of m2 increases, the gap will increases. Okay, where m1 is the lighter mass and m2 is the heavier mass. And we also said that when m1 is equal to m2, the gap will disappear. Okay, hope you understood the point. So you can see there is a relation like this as well, that is this frequency gap is actually proportional to root m2 by m1. So you can see that as m2 increases, the gap will also increases. If m1 increases, the gap will reduce, and if m1 is equal to m2, this gap will be equal to 0. The frequency gap will be 0. So that is a expression I was telling about. Okay, and in monoatomic lattices we can only see acoustical branch, that we have discussed earlier. No, okay, acoustic, that means sound waves മാത്രമേ അവിടെ ഉണ്ടാവുള്ളൂ. acoustical branch മാത്രമേ ഉണ്ടാവുള്ളൂ monoatomic latticeന്റെ കേസിൽ. But in diatomic lattice we have both optical and acoustical branch. Okay, so it is necessary for an optical branch um, to for an optical branch to be happen, there will be at least two atoms should be there in a primitive unit cell. If there are two atoms in the primitive unit cell, then you can expect an optical branch. Otherwise, if there is only monoatomic lattice, you can see only acoustical branch. So that is also an important aspect here. So here you can see in optical branch how the atoms are actually moving. Okay, so you can see that is a representation of how the atoms are moving in a case. Okay, so we were discussing that point is that for a monoatomic case you will only see acoustical. Okay, for a diatomic case you can see acoustical plus optical branches. Okay, so in optical branch there will be two atoms which is moving in opposite direction. So hence the center of mass in the optical branch will be remains fixed. Okay, which remains fixed in that case. Okay, so optical wave means we already say that that is light wave. So an electromagnetic wave is incident on a lattice, then you will be getting optical wave. If a sound wave or a mechanical wave incident on a lattice, then you will be getting an acoustical wave. The discussion we have done in the previous lecture. Okay, and so you can see some more expression related to this one, observation that is related to here. That is, if you consider uh, if you consider a NaCl lattice here. In NaCl we know that that is an example of diatomic lattice because there is sodium is there, and we also having chlorine is there. So you can see that the chlorine will be moving upward direction, and the chlorine will be going downward direction, and the sodium will be moving upward direction. So it will execute a motion as we have seen in the earlier scenario. Okay, like a motion will be executing like this. Okay, where chlorine having heavier masses, sodium will be having lighter masses, and M1 M2 will be is different. But in optical wave case, the center of mass is remains fixed. In optical branch, the center of mass is fixed, as you can see. But in acoustical branch, center of mass is not fixed, so it is move with the atoms. So it is the vibration, the corresponding vibration will be moving with the atoms. Okay, so normally the optical branch can arise in different crystal like sodium chloride, zinc sulfide, gallium arsenide, where one atom will be heavier compared to the other one. So it is a scenario of a simple, it is a scenario of a diatomic lattice. Now if you consider another two set of atoms, that is called diamond and cesium chloride. Okay, so it has a simple cubic structure, cesium chloride especially. So in cesium chloride you can't see any optical branch there. Okay, it is actually a two atom basis. So one will be expecting that there will be a optical branch will arise there, but in normal scenario you won't see any optical branch in the case of cesium chloride and diamond. Okay, in these two atoms you can see this kind of optical branch will be arising here. And now what we are going to address is that we will be addressing, we have a number of branches in solid. Okay, so what is how many number of branches will be there in the solid? So for that we can actually take another representation. Okay, so here we'll number of branches in the solid. Okay, so number of branches, if there are p atoms in the primitive unit cell, so we have assumed that we have p number of atoms in the primitive unit cell, or we can say that it is a p atom basis. The number of atoms in the basis actually we can represent, and you can see how many branches will be there, how many acoustical branches will be can arise over there. So you can see here a table which is actually representing the branch in one dimensional, two dimensional, three dimensional, and number of acoustical branches. For one dimensional that is 1, for optical that is p minus 1, and this will be 2, and this is 2p minus 2. So you can see that expression here. Okay, so for a monoatomic lattice, if you see this expression, that is p is equal to 1 monoatomic lattice, there will be single atom scenario. So you can actually see p is equal to 1, and acoustical will be 1 that scenario, then optical will be what, it will be 0 for a monoatomic. So number of atom is 1, and for a diatomic lattice the number of atoms is 2 in the primitive unit cell. So acoustical will be 2, and optical will be what, that is 2p minus 2 scenario. So this is how the number of branches in solids will be C. And now if I am interested in the number of vibrations, vibration modes. Okay, so you would have discussed in vibration modes in your couple of experiments that you have done in lab. So there you can see, uh, if you see the number of vibration, the possible vibration in the case. So let me have p number of atom in the unit cell, and the total primitive unit cell is n. Total number of primitive unit cell in solid is n. So you can see that the total number of atoms will be pn. Okay, and that case, if there is one dimensional case, we have p n atoms. So the acoustical and optical range representation, you can see one is n, one is p minus n. So you can see that for a one dimensional monoatomic lattice, we know that the solid contains n number of atoms. The total number of modes will be what, n. So the acoustical will be n, the optical will be 0. For a one dimensional diatomic lattice, okay, there you can see that the total modes will be 2n, and the acoustical will be n, and the optical will be N as well. Okay, there will be optical branch and there will be acoustical branch as well. So these are the discussion we need to discuss when we discuss about frequency of vibration or vibration of one-dimensional diatomic molecule. Main point is that in one-dimensional diatomic molecule, there will be two kind of waves will originate. One is optical wave or optical branch, or one is acoustical wave and acoustical branch. And the main exercise we have done today is that we just try to identify the frequency of vibration for optical wave and acoustical, and we have considered the limiting cases to address what is the frequency of vibration in different limiting cases. And finally we were discussing about the number of modes of vibration and number of branches in solids, how it will be there. So okay, so these are the discussion we need to address in this particular session. So with that I'm just winding up today's session. So in next class we'll be addressing about condensation of elastic waves, or rather we'll be discussing about phonons. Okay, thank you.